Gradient descent is an iterative optimization algorithm used to minimize the cost function or error in machine learning models. It's a fundamental algorithm in the training of models, particularly in the context of supervised learning. Here is the general setup of the gradient descent. The whole algorithm focuses on a so-called objective function, also often called a loss function or a cost function, which really measures the difference between the predicted output of the model and the actual output. And the whole idea of the gradient descent is to find the model that gives you the smallest possible value on this loss function. And the algorithm starts with an initialization step where the parameters are initialized to some values, whether randomly or with some predefined values. And then we have an iteration where over a number of steps we do two things. On one hand, we do a so-called gradient calculation. And what this means is that we are going to look at this objective function and we are going to check in which direction this objective function has the steepest, the biggest decrease. And we are going to use this calculation to update these parameters. In other words, we are going to decide in some way how should we change our parameters with some small values in such a way that we get a big decrease, as big as possible, in the objective function based on these gradient calculations. And then we are repeating these steps 3 and 4 until the objective function tends to stabilize. It looks like we cannot really minimize it any further. Or, for example, if we just ran out of time, we reach the preset number of iterations. I'm going to discuss each one of these steps separately and give some more details on how they work. So here is a little bit more about this loss function, also called cost function. So this is a function that you calculate over the entire training data set, and the values of these functions depends on the parameters of the model. It really measures how well a model does on a given set of parameter values. So, for example, if you have this model phi that depends on these parameters, W0, W1 to WD, in some way that I don't really specify on this slide. So the cost is going to be a function that depends exactly on these parameters W0 all the way to WD. Very often this cost function is chosen to be the mean of squared errors, but much of the discussion in this video is going to be on a general level for any cost function or loss function you may want to choose. And so the objective of this gradient descent is to find the parameter values that minimize the value of this loss function. So this is a visual way to look at how gradient descent works. So if you look at the shape of your loss function, you're going to be interested in the smallest possible values of the loss function. So in other words, you are going to be interested in these minimum points, and in general you may have several of them. In this particular illustration, there is one here and there is one there and there is one that you don't see but you guess somehow from the illustration just behind this peak. And the objective of the gradient descent is to find one of these, hopefully, the global minimum, but it could also be that it ends up in one of the other minima. So the way this is working is that it will start with some random values, W0, W1, WD, and what this means really on this visual illustration is that it's going to do a search for this minimum point starting somewhere in this landscape, and let's just say that choosing your initial values will make you start your search from this point in the landscape. And then what this algorithm will do is, in each step, is going to check the position in the landscape and is going to check in which direction do I have the steepest descent. And for example, on this landscape, it is as if you are on that part of the mountain and you are looking to see in which direction you have the steepest descent over the next step. And you might decide, for example, that here, this is your steepest descent, and the idea is that you're going to make a small step in this direction, and you are updating your parameters along this direction of the steepest descent, and so your new parameters will bring you to this location of the loss function on this landscape. And then you are evaluating again, what's the steepest descent in this particular point, and maybe you decide that this is my steepest descent, and you are updating your parameters again, and that means that now in this landscape you are here in this point with your loss function. Again, you are estimating the steepest descent, and maybe that's going to bring you to this point, and so on. You are doing this over and over again until you reach a minimum point in the loss function, or as I said, you run out, you just reach the maximum number of iterations you set for yourself. And of course, I mean, as you can see in this illustration, the difficulty with this numerical algorithm, not just gradient descent, but really any numerical algorithm, is that you might not get the local minimum. Depending on where you start your search from, you might end up in one of the local minima. So you might get a solution that's not the absolute minimum of the loss function. So choosing the initial point in general is important. It might lead you to a solution that's better than solutions that start from a different initial point. I'm going to come back to this point and also argue that it depends a lot on what kind of loss function you are choosing, because there are choices for loss functions that in fact are easier from this perspective. There is only one minimum point for a certain type of loss functions, but I come back to this point. So if I go again to this idea of assigning values to your parameters. So again, the initial step was where you assign some initial values for your parameters, for example, random values, or maybe you want to set them up to some predefined strategy, for example, make them all 0. And then the way you are updating your parameters is actually written in this rule. So what this means is that you are going to calculate the partial derivative of the loss function with respect to each one of these parameters, and you are going to use this partial derivative in this rule to update your parameters. So what this rule says is that the new value of each one of the parameters is going to be calculated in this way. You start from the previous value of the parameter, and then you are going to do this calculation where you say w minus, and then you have this partial derivative of the loss function with respect to that parameter that you are updating. This is also multiplied with a small positive constant. This is called the learning rate, and I will discuss in a moment what's the purpose of this learning rate. I want to comment a couple of things, and then I discuss one example where I choose this loss function to be something concrete so that we can see how these updates are done. But in general, what I want to comment is that this idea that you take the partial derivative of the loss function with respect to the parameters corresponds exactly to the intuition we had in the visual setup of the previous slide. It's really about this concept that you're going to take the steepest descent in the loss function. This learning rate is really giving you the amplitude of each update step. So again, connecting to the visual intuition we had on the previous slide, having a larger alpha is going to give you a larger step in the direction of the steepest descent. And one more comment I want to make is that these updates you are making in here, they are going to be simultaneous updates over all your parameters. So you first calculate the partial derivatives of the loss function with respect to each one of the parameters, and then you are making this simultaneous update over all your parameters, and then you repeat this whole thing once again. In other words, you again calculate what's your loss function, you calculate the partial derivatives, you are updating all of them simultaneously one more time, and so on. So I want to give an example so that you get a feeling for what this update based on the partial derivatives is going to give you, and why this actually makes sense. So in my example here, I'm going to just take the case where I have one single numerical parameter w, and the cost function is going to be a quadratic function, just so that you can see it easily visually, and we have a sense of where the minimum is, and we will have a sense of where these updates are going to take us. So this cost function is the quadratic function in this case, and I'm using exactly the update rule that's used generally in the gradient descent algorithm. So here is my example. Again, the cost function in my example is going to be this quadratic function, and you are going to have this initial step, and let's say that maybe you are starting in here. And your update rule is going to tell you, hey, you need to calculate the partial derivative. In our case, because we have a single parameter, that's the standard derivative of the loss function. Now, the standard derivative is really connected to the tangent that you are drawing through this point, the tangent to the curve that you are drawing to this point. And this tangent being, with a positive slope, it means that the partial derivative is a positive number. And so this update rule is going to be something like this. You take the previous value of your w, so this was the first value that we started with for w was this, and then it's going to be minus the partial derivative, which in our case, because this is an increasing line, it has a positive slope, so this partial derivative is going to be a positive number, and alpha is a positive number, so it's going to be w minus something positive. So what this means is that this update is going to tell you to update your value w to a smaller value, which means that the new value of w based on this update in the gradient descent is going to be right here. And this seems to work fine, because this is going to imply a smaller value for the loss function g of w. We started from this much loss, and with this update that we have in the gradient rule, in the gradient descent algorithm, seems to take us to the right direction. We get all of a sudden, a smaller value in the loss function. And this also applies if you start, for example, on the other side of the slope. So let's say that you start somewhere here, so your initial w is here. Again, the update rule in the gradient descent is going to say, hey, you need to take a look at the partial derivative. Again, my point with the partial derivative is that this is connected to the tangent through this point, and in this case, on this part of the curve, the slope of the tangent is negative. This is a decreasing line. So the partial derivative in this rule is going to be a negative number. Alpha is always a positive number, so this product is going to be a negative number. And with a minus in front, that's going to give us overall an increase in w. So the gradient descent is suggesting that in this case, you are updating your value w to a larger value. So that means that you started from here, and now you are going to update your w here, which again seems to go in the right direction. We started with this much loss in the initial set of choice for w, and now the update rule is going to give us a smaller value in this loss function. So intuitively, this update rule in the gradient descent based on the partial derivatives seems to work fine, at least for this example that I'm using here with the quadratic function. With each step, it seems to bring us closer to the minimum. One point I want to make is about this, the learning rate, and there are 2 points that I want to make in here. If you are choosing a learning rate alpha that's too small, I want to show you what the effect is, and then also this one, what if the alpha is too large. So, like I commented, I mean, the alpha here is going to give you the amplitude of your update step. So, partial derivative, it is what it is. But the difference, I mean, the amount by which you are updating your parameter is going to be dependent on how much alpha is. If alpha is too small and you are starting, say, from here, then you are going to have a very, very small update, in W. And so that means that, you are going to have a sequence of values that are very close to each other and they go in the right direction, but the update is going to be very slow. The convergence of your algorithm is going to be very slow. That means that it might take a long time to actually train this model to reach the minimum point. The problem with having too large of a learning rate is different, and as a matter of fact, it might be so that this is going to make your algorithm even not converge at all. And you can see this again visually here. If I'm starting here, the update based on the partial derivative is going to mean that I have to increase my W. But if alpha is too large, you might have such a big increase in your W. So from this value of W, your algorithm based on this very big alpha might say, hey, how about you increase somewhere here? And that means that you might actually go to a value of the loss function that's larger than what you started with. And then you are updating again based on the partial derivative at this point. This partial derivative is even bigger than what we had before, and again you have a large alpha, so that might actually take you to an even larger value of your loss function, and so on. So instead of actually getting to a minimum, having a large alpha might imply that your algorithm is diverging. In fact, it never gets close to the minimum point. And just one additional point I want to make in here, it's also about this partial derivative. As you are getting closer and closer to the minimum point, the partial derivative is going to be closer and closer to 0. So your algorithm, as you get to values that are close to these minimum points, is going to stabilize to some extent. The updates are going to be smaller and smaller if the partial derivative around this point is closer to 0 as it should be. I mentioned that in practice, most of the time people use for the cost function the mean squared error. And there is a good reason for this. The special advantage of the mean squared error function is that it only has one minimum. And in general, we say that this leads to a convex function. And in general, convex optimization problems have a single minimum. So that means that your numerical algorithm, as long as you are careful with your choice of the learning rate alpha, is going to lead to the global minimum. So just to summarize, the setup for the gradient descent, and I'm going to show this in the case of linear regression and in the case of the mean squared errors, is going to be this, that you have the features in your data point. So each data point has the features, and you have also the label for each data point. You have a number of data points, and you are interested in a linear model, in a linear regression, meaning that the function that you are looking for is of this type. It's going to give you just a linear combination of the features. And the parameters of this linear regression model are collected in this vector. They are W0, W1, all the way to WD. And in case you are choosing your cost function to be the mean squared errors, that means that your cost function is going to have this form, is going to be 1 over 2 times n, sum of all of these differences between the prediction of the model and the real label, 2 power 2. And if I'm just replacing who this prediction is, I'm just replacing it with this form, it's going to be 1 over 2n, sum, and then you have this expression, the linear combination in terms of the features, minus the label for that data point, and that's going to be squared. And so what gradient descent is telling is that you should update your parameter value starting from the initial choice of the values to be according to this rule. So it's going to be W minus alpha times this partial derivative. And what I want to do on this slide is just to show you who these partial derivatives are, And this I can easily do because I have a very simple form for the cost function. So just to explain how easy in fact this gradient descent rule is in this case for the mean squared error. So the way this goes is the partial derivative is calculated with respect to each one of these parameters w0, w1, wd. The expression is just a little bit different for w0 than for the other one, simply because w0 is the free term in this linear model. So I'm going to calculate that separately, and then I'm going to show you the partial derivative for the other ones. So the partial derivative with respect to w0, so the partial derivative of the cost function or the loss function is going to be like this. So you are just checking where your w0 appears, and it's clear it's in this term. So we apply the derivation rule. So this is going to be equal to 1 over, and then I'm going to have 2n, but in fact this power 2 from this term is going to give me an additional 2 here in front, which cancels out this 2. So I'm going to have just 1 over n sum. And I already anticipated that when I calculate the derivative of this term, this power 2 disappears, it goes in front, so I'm left with this term to power 1. And then it's going to be multiplied with the partial derivative of this term with respect to w0. But w0 is only here, so that's going to give me 1. So in other words, I have this parenthesis here times 1. And this parenthesis is exactly phi w of xi minus yi, and this is a sum from 1 to n. So that's all there is to it. The other derivatives are almost the same with just a small difference. So if I'm calculating all the other ones, say wk, where k is from 1 to d, so this is going to be exactly equal to, and again I'm going to check where is my wk, so it's in one of these terms. So that means that I'm going to calculate the partial derivative of this entire term. So that's going to give me this 2 that goes in front and cancels out with this 2. So it leaves me with 1 over n. Then I have my sum. And when I calculated the derivative and that gave me 2, I'm left with this whole parenthesis, which is just like before, phi w of xi minus yi. And then I also multiply with the derivative of this term with respect to wk. And wk is going to be one of these terms, so when I calculate the derivative, I'm going to be left exactly with this component. So that's going to be times xki. So in other words, the kth feature of the data point xi. And again, that's all there is to it. That's the partial derivative, and that's what we use in this update rule.